Alright, so we're starting a new topic on indices. And to get an idea, you guys will be more familiar with this than you probably realise, but an index is just a power, or sometimes called an exponent as well. So here I've got 2 to the 5, which simply means we've got 2 times 2 times 2 times 2 times 2. So we have 5 factors of 2 there. Now we could go and write that as 32 as well. So that's simply by multiplying all those 2's together. And what we would call this our base. 2 is our base. We would say 5 is our index or our exponent. Index just being the single of indices, or indices being the plural. We'd call this one here expanded notation. And we call this as a base numeral. Okay, so that's just sort of a little bit of notation there. Now, more commonly, we'll probably see this when we start dealing with algebraic terms, so something like a cubed. Well, that just means a times a times a. Now, of course, here we have a base of a power of 3, and we can write that in expanded notation as a times a times a. We really can't write it as a base numeral, though. There's no other way to write something like that. So if we've got a numerical base, we can normally write it as a base numeral, but if we don't have a numerical base, or we've got a letter, a pronumeral, we're just going to end up writing it as a cubed in simplified form. So we have a couple of rules, and you'll probably be familiar with these. Our first one is that if I have 2 common bases, so I've got a, let's say a cubed times a to the power of 4, well, I could write that out as a times a times a, well, that's a cubed, times a times a times a times a. I have 7 factors of a there, which is a to the power of 7. Okay, now remember, each of these here has a little invisible, non-written power of 1. Okay, so any term has a power of 1, unless it has some other power written. So what that means is if that I have common bases, the same base, if I have a to the power of m times a to the power of n, where m and n will just be numbers, that means I just add those powers. Okay, if I'm multiplying terms and they have the same base, if I'm multiplying and they have the same base, I can just add those powers. The second of these rules, and it works in kind of the opposite direction, is that if I have something like b to the power of 6 divided by b squared, well, I can rewrite that as a fraction. I can write that as b to the power of 6 over b squared, which is b times b times b. You see why it's good to have these rules, because it will save us a lot of time and writing. Now what ends up happening is I've got b divided by b, which of course doesn't give me 0, it doesn't just disappear, they give me 1 over 1. Same deal with those ones, I get 1 over 1. So I'm left with b times b times b times b, which is b to the power of 4. So our second rule is that if I have, I'm going to pop this one over here, if I have common bases and I am dividing, I can subtract the second power from the first. Now again, it must be the same base, same rule applies, but obviously if I am dividing this time, I am subtracting. If I multiply with the same base, it means I can add. If I end up with something like a cubed times b squared, they don't have the same base, I can't just go and combine those. It's a little bit like terms when we start adding and subtracting them, but rather than adding them, we are going to be multiplying and dividing them. Alrighty, let's do a couple of examples here. Alrighty, so if we start off with a couple of nice basic ones, I'm going to have 5 to the power of 3 times 5 to the power of 4. Now, an easy way to get caught with this question is to go and say, well, 5 times 5 is 25, and then I add to my powers, and so it's 25 to the power of 7. But In fact, we obey the same rule as if these were both a's. If it was a cubed times a to the 4, you'd know that it'd be a to the 7, so it behaves no differently. If we're writing an index notation, that's just 5 to the power of 7. Our base doesn't change. Similarly, if we have something like 3 to the power of 5 divided by 3, well, this 3 here has an invisible power of 1, so it becomes 3 to the power of 4. Let's have a look at another one. I've got p to the power of 6 times p to the power of 3 times p squared. Well, just because we're multiplying 3 terms, that doesn't actually change anything as long as they have the same basis here, which they do. So that'll be p to the power of 6 plus 3 is 9 plus 2 is 11. Let's have a look at another one. B to the power of 5 times b squared divided by b. Okay, so we've got a multiplication and a division here. So b to the 5 times b squared is b to the 7 divided by b. It's nice here, they all have the same base. Well, again, this b here has an unwritten invisible 1, so this just becomes b to the power of 6. Again, a trap people can fall into is something like this, is looking and saying, oh, well, I'm dividing by b, so therefore this b here, it must disappear. Well, that's not how we work. We could write it out as a big long fraction, we don't need to, but we would find b is actually multiplied 7 times in our numerator, divided once, which means we're left with b to the power of 6. Have a look at another one here to bring in some numerals and some powers. So if I've got 3m cubed times 5m squared. Alrighty, well, we treat this no differently. Our m's have the same base, so that's going to be m to the 3 plus 2 is 5. Well, these numbers, they actually behave no differently than they normally would. We just have 5 lots of 3, which is 15. Okay, so our numerals behave exactly like numerals, and our terms with these powers or these indices behave as they do with our laws for multiplication. Let's have a look at a couple involving division. If I've got m to the power of 8 divided by m to the power of 5. Alright, well, we know that we could write that out as a extended fraction, don't really need to, but it's a division, so I'm going to just subtract 8 from 5, 5 from 8, and I get m to the power of 3. If I've got n cubed divided by n to the power of 7, well, this time I'm going to subtract 7 from 3, my base still stays as n, but I end up with n to the minus 4. Nothing wrong with having a negative power. We will look at actually what that means next week, maybe later this week, but there's nothing wrong with having a negative power. The power that we're dividing by here is larger, so we're going to end up with a negative. Here's one involving a fraction and some multiplication, so I've got 3f squared times 8f to the 7 over 4f cubed. Alright, straight away I notice same bases everywhere, f. So the numerals are going to behave as numerals, so 8 lots of 3 are 24. And let's just get it as single terms on top and bottom, so that'll be f to the 9 and 4f cubed. Well, we're just going to literally look at it as 2 parts. Okay, so we'll deal with 24 over 4 is 6, and f to the 9 divided by f to the 3, that's what this really means. F to the 9 divided by f to the 3, which is f to the power of 6. So we literally just treat our numerals and our indices as separate entities. A couple of harder ones here. Main thing to look out for here is common bases. And remember that if we're multiplying, we just add those powers, and if we're dividing, we subtract the second power from the first.